A team at Huawei just compressed the KV cache of a reasoning model down to 2 bits per element, and somehow the model still solves AIM math problems at 60.7% accuracy. The full precision version gets 61.1. That's a 1 to 2 bit precision drop, and the gap is basically a rounding error. Okay, so the paper is called Kvarn, dropped on arXiv on June 2nd, 2026 from Huawei's Computing Systems Lab. 6 authors, led by Lorenz Muller. The full title is Variance Normalized KV Cache Quantization Mitigates Error Accumulation in Reasoning Tasks, which is a mouthful, but it's actually pointing at a real problem nobody had really called out. Here's the setup. Reasoning models like Kvarn 3, the O-series, R1 style models all use test time scaling, which is a fancy way of saying they think for a really long time before answering. AIM problems can pull 12,000 tokens of chain of thought easily. And every single one of those generated tokens has to live in the KV cache. That cache grows linearly with sequence length, and in FP16 it gets huge. At long context, the KV cache eats more memory than the actual model weights, which is kinda insane when you think about it. So people have been quantizing the KV cache. Kivi, Quaret, KV Quant, Turbo Quant, Polar Quant, tons of methods. But Kvarn points out something everyone kind of missed. All these methods are benchmarked on prefill tasks. You feed in a long document, you quantize it once, you ask a question. Static. Clean. Easy. But that's not how decoding works. During decoding, the model generates a token, writes it into the quantized cache, then generates the next token based on that quantized cache, and writes that into the cache too. So now you have quantization error feeding into the next quantization step, feeding into the next one. Errors accumulate, and they compound exponentially over a long reasoning trace. The Kvarn authors built a thing they call pseudo-decode, which simulates this regime. And under pseudo-decode, every existing method looks dramatically worse than its paper numbers suggest. Kivi's reconstruction error on Qwen 34 billion grows steadily across context length. Kivi's ARNS stays basically flat. Okay, so how does it actually work? There are 2 ideas glued together, and both matter. First idea, Hadamard rotation. This is borrowed from Quarat and Quip. The intuition is that when you have outlier values in a matrix, naive quantization wastes most of your bit budget representing those outliers, and the normal values get crushed. If you rotate the matrix with a Hadamard transform, you smear the outliers across all channels evenly. Suddenly the distribution looks uniform, and your 2-bit grid actually fits the data. Think of it like packing a suitcase. If you have one huge shoe and a bunch of socks, the shoe defines the suitcase size. Hadamard rotation is like shredding the shoe and the socks together into confetti, so everything fits in a much smaller box. That handles outliers along the channel dimension. But here's the twist. Kvarn authors realized that the actual killer error in autoregressive decoding isn't directional. It's magnitude-based. They decompose the total quantization error into 2 pieces. Magnitude error, which is how wrong the norm of the token is, and directional error, which is how wrong the angle is. And when they look at the top 1% of worst errors, it's almost all magnitude, like 90+% magnitude error. The Hadamard rotation only handles channel side stuff. Per token magnitudes still get blown up by the rounding step. So they need something else. Second idea, dual variance normalization with a Sinkhorn style iteration. Sinkhorn is an algorithm from optimal transport that takes a matrix and iteratively rescales rows and columns until both row and column sums hit a target. Kvarn does the same thing, but with variance. They iteratively rescale the K matrix along the token axis and the channel axis until both axes have unit variance. Why iteratively? Because if you only normalize one axis, the other axis blows up. If you normalize tokens, the per-channel kurtosis explodes. If you normalize channels, the per-token norms go wild. The iteration finds a fixed point where both are tame at once. They run this in log domain for numerical stability. Algorithm is in the appendix. It's like 10 lines. The whole thing is calibration-free, meaning you don't need a dataset to fit anything, you just compute it from the tile of the cache you're about to quantize. The cost. 1 extra floating point multiplied per token per channel at dequantization time. That's it. Hadamard adds a fixed cost per channel chunk. They process the cache in tiles of 128 tokens by 128 channels, which lines up with how attention is computed anyway. The GitHub repo ships as a native VLLM backend. You enable it with one flag --kv cache dtype kvarn k4v2g128. That means 4-bit keys, 2-bit values, group size 128. Triton kernels, no custom CUDA, so any precompiled VLLM wheel works. Results. This is where it gets fun. On AM 2024 with Kvarn 34B at 2-bit precision, Kvarn scores about 60.7%. FP16 baseline is 61.1. KVI at the same bit budget falls to 55.5. Coro 56.7. KVI quant collapses to 40. So Kvarn basically gives you FP16 reasoning at 1/8 the cache memory. On MATH 500, FP16 is 82.6. Kvarn holds 82-ish. Kiwi drops to 77.8. KV quant tanks to 67.5. Human eval, same story. iEval, same story. Llama 3.18 billion and Phi 414b, same story across the board. The average bits per element is 2.3, which counts the high precision scale vectors. So we're talking roughly 7 times compression versus FP16, and the model just keeps reasoning. Now, is it cherry-picked? A little. They mostly show reasoning benchmarks where token magnitudes drift because that's exactly where their method shines. On prefill style tasks, the gap to Kiwi is much smaller. They're honest about this. The pseudo decode setting is their own invention, and yeah, it just so happens to favor their method. Convenient, but also, fair, because it's closer to how reasoning models actually run in production. What changes? A few things. For people running inference, this is straightforward gains. Triton, no custom kernels, 1 flag in VLLM. If you're serving Kvarn or Llama with reasoning enabled, you can probably triple your context length on the same GPU, like tonight. The repo claims throughput above FP16, which sounds fake but actually checks out because memory bandwidth is the bottleneck and you're moving 1/4 as many bytes. For people building reasoning models, this is a hint that the next bottleneck isn't compute, it's KV cache. We've spent 2 years optimizing attention with flash attention and MQA and GQA. The next axis is bit width. For other research labs, expect a wave of follow-ups within weeks. Sinkhorn-style normalization is the kind of trick that immediately generalizes. Someone will try it on weights again, someone will combine it with TurboQuant-style codebooks, someone will push to 1 bit. For consumers, this is invisible but real. It means your local Kvarn on a 3090 can suddenly think for 40,000 tokens instead of 10,000. Long agent runs, deep research, coding agents that don't forget half the file, all get cheaper. Caveats. The paper only tests up to 14B parameters. We don't know how this scales to 70B or 400B MOEs. The pseudo-decode setup is a simulation, not real decoding, so there's wiggle room. And accuracy on AIM has run-to-run noise of 3 to 7 points, so some of the headline gaps are tighter than they look at first glance. Also, there's no comparison to TurboQuant at matched bit budget on reasoning tasks specifically. TurboQuant is the strongest prior baseline, and they only compare it at 3x3 bits, which is twice the budget. Side-eye. The closing thought is this. We spent the last year obsessing over how big the models can think. Longer chains, longer context, more tokens. Kvarn is a quiet reminder that the memory wall is just as important as the compute wall. And sometimes the fix isn't a new architecture, it's an iterative rescaling trick from 1967, applied in the right place. If you would like to hear and see the latest news about LLMs, then like and subscribe.